All right, we're going to talk about limits. And first, I'm going to give a disclaimer that I am doing laundry in the background. So at some point, you're probably going to hear the machine going, whether it's telling me it's done or just shaking the whole house. So, apologies for that. So, limits. They're the backbone of understanding all this calculus stuff. So, really what a limit is in like basic terms is as we are approaching some x value, the question is, what is the y value doing? Is it approaching a y value? Is it approaching infinity, negative infinity, that kind of thing? So there's a couple different limits. We got a right hand limit, a left hand limit, and a general limit. All right. I'm going to do the general limit first. I should have listed it first. But if I'm going to write it out, that would be the limit as x approaches c for f of x, where c is just some value. So verbally, that's just the limit as x approaches c, and then is whatever that limit is. So if we want to talk directions, the left and right, the notation is going to be a little bit different. So for the right hand, we'll have the limit as x approaches c, and I'm going to put a plus sign here to denote, hey, we're going to look at from the right side. So verbally, we could say this is the limit as x approaches c from the right. So for the left, we'll put a minus sign. So it's the limit as x approaches c from the left, right? So sometimes we might not have a specific value that we're going to, but we still can look at what is happening. Like, what are the y values doing? So think of rational functions here, where they're discontinuous. Finding these limits will help us find where it's discontinuous, right? Just look at this picture here. We don't know from where we're standing maybe where like the height is, but we can see that we're building this bridge or whatever this is. Bridge. We can tell where it's going to be finished because from the left, it's going here. From the right, it's also going here. So it's going to have to finish in the middle there. Okay? So we have a little theorem here, the limit existence theorem. So just a formal way of putting it. So the limit as x approaches c of f of x exists if and only if the limit from the left equals the limit from the right, and it's a value, a real number. Okay? So for a limit to exist, the left hand and the right hand side have to exist, and it has to be the same. Okay. So let's look at evaluating them. There are many different ways to evaluate them. So from a graph, I would argue it's the easiest way because it's very visual here. I might have to keep scrolling to answer all these questions. So these first two, A and B, are just asking for function values. They're not asking for limits yet. So f of 2. We're looking at what is the y value when x is 2. So I have a closed circle here at -1. And then f of -1. F of -1, I have a hole here, right? But I do have a closed circle up top. So f of -1 is 4. Now we're going to get into some limits. So I want the limit as x approaches 4 from the left. So here's what I do. I go to x equals 4. I draw a little dotted line. And then we want the directional side. So we want from the left. So coming from the left, as we're approaching 4, what is the y value doing? It's approaching 3. Okay. I'm going to erase my drawings each time. So the next one is the limit as x approaches 2 from the right. So I draw my dotted line here, and I'm approaching 2 from the right side. So I know from the right side I have a hole at x equals 2. But the function itself is still getting close and close and closer to the y value at that point. Right? So I know the function value doesn't exist, but we can still have a limit that exists. It's 1. So even though, again, the function value doesn't exist, the function values, as we're getting closer and closer to x equals 2, the values are getting closer and closer and closer to 1, even though they're not going to reach it because of the hole. But the limit still exists. Now we're going to do 2 from the left. So it's this side. So these y values are approaching -1. And so now it wants the general limit. So the limit as x approaches 2, just in general for the function. Well, remember, for the general one to exist, we have to have the left and the right match. So because we have 1 versus -1, those are not the same. So we would say does not exist, or DNE. All right, let's erase my drawings here. We're now going to look at -1. So I draw a little dotted line. We want from the left. So from the left, I've got it approaching 2. From the right, also 2. So then the general limit, because it matches left and right, is 2. So even though the function value is not 2, it's okay for the limit to still be 2. Now we want -4 from the left. Ooh, this is a good one. So here's -4. From the left, I don't have any function on this left side to give an answer. So it does not exist. Or just say undetermined. I can't, there's nothing to the left telling me. Like this function here on the right side is telling me we're going off to -infinity, but there's nothing to the left side of -4 telling me what, the function's potentially doing. So maybe I should say undefined, because the function is undefined. Either way, I would accept both answers. All right, -4 from the right. All right, so in this case, we are having a function to the right of it, and it's approaching 2. All right, so the general limit here, we can't say exists, does not exist, because that left-hand side doesn't exist. All right. And now this one here, we've got the limit as x approaches 5. So I'm going to erase my drawings here. Now, this is the general limit. It didn't separate it nicely like all the others have. So I do need to check the left and right side, right? So from the left, I would say -2. It's going, to -infinity. And then from the right, if we go back the opposite way, it's also going to -2. So I would say the limit is -2. And then we're looking at x equals 0. So again, doesn't give direction, so we need to check both anyway. So from the left, -1. From the right, also -1, and it matches. So the limit is -1. Right, there's some scenarios here where limits can fail to exist. So 3 different cases. So I'm going to scroll into this one. So case 1. So the limit will not exist if the limits differ on the left and right. We had seen above where that was the case, right? So this says justify why the limit does not exist at x equals -1 for this function. So we could say, hey, the limit as x approaches -1 from the right. Let's see, from the right, it's 1. Oh, I don't know, I'm spelling out the full word. Limit as x approaches -1 from the left of the function is -1. So you can see the left and the right don't match. So there's the justification. All right, this next one, it's hard to see in this picture, but this case number 2 is if there's any oscillating behavior. So you can see that, and here, I'll try and draw it in a different color here. It's like switching back and forth, back and forth, back and forth. Basically infinitely many times right there. It's, again, hard to see, but the pattern is that it's, flip-flopping, flip-flopping. And we can test the value. So this is the function, sine of 1 over x. We can test the values as we get closer and closer to 0. I could plug in maybe, I don't know, x equals 0.1. That's arguably close to 0. So we'd have sine of 1 over 0.1. Okay? And so that would be from the right side. And this will be a negative number. And if I plug in x equals, how about negative 0.1? So sine of 1 over negative 0.1. That actually gives a number that's greater than 0. Right? So from the left and the right, if one's positive and, oh, that's backwards. If one's positive and one's negative, those are not going to be the same numbers. So that limit does not exist. All right, and now this third case is unbounded behavior. So if it's going off to the infinities. Okay. So, all right, as x is approaching 2. So the limit as x is approaching 2 from the right for our function is infinity, right? And the limit as x is approaching 2 from the left is also infinity. But, so, okay, we would say, hey, infinity and infinity are the same, right? So we would say, hey, the limit as x goes to 2 of the function is infinity. But, by definition, infinity is not a real number. So with that existence theorem, remember it was equals L, where L is a real number. So this infinity just describes behavior of the function. So it's tending towards infinity. But again, it's not a real number, so we can't say that the limit exists. All right, we're going to get into some properties of limits, okay? So there's different things we can do mathematically with limits based off of these properties. So we're going to let b and c be real numbers. N is a positive integer. And then f and g are functions where, all right, the limit as x approaches c of f of x and the limit as x approaches c for g of x, both of those exist. So here are some rules We have a constant rule here. If we have the limit as x approaches c of some constant, that limit is going to be that constant. There's an identity rule. If it's just x, then as x approaches c, it is just that c value. And we have a coefficient rule. So if we have the limit as x approaches c of some function that's multiplied by b, where remember b is a real number, we can actually, it's almost like we can pull it out as a GCF and deal with it later. And like multiply it by that limit of the function. The sum or different rule, I should say difference, but it's okay. We can separate if two functions are being added or subtracted. We can separate their limits and add or subtract them based on what it is. If it's plus, then we can add the limits. If it's minus, we can subtract the limits. All right, the product rule for limits says if the two functions are multiplied, we can separate and find the limits individually and then multiply those limits. Same with the division. We can separate it with division. The power rule, we can find the limit of the inside and then apply the exponent. And then the composite function, we can find the limit of the inside and substitute that into the function. And then we have the root rule here, similar to that exponent one, the power rule. If it's taken to the nth root, we could actually just find the nth root of the limit. Right? If the right side exists. All right. So let's use these properties. So we have two functions here, f and g. We're going to use our properties to see if these exist. All right, we want the limit as x approaches 3 from the right. And we have a sum here. So I can separate it and say the limit as x approaches 3 from the right of f of x. And we can add in the limit as x approaches 3 from the right from g of x. So for f of x, here's 3. And we want from the right. So from the right, we are approaching 6. And then on g of x at 3, from the right, we are approaching 8. And 6 plus 8 is 14. All right, I, for the purpose of these notes, am going to separate out in one step these limits. So I can separate it with that subtraction. But then within that subtraction, I have numbers out front that I can pull out almost like a GCF in a way. So I can say this is 3 times the limit as x approaches 5 for f of x minus 2 times the limit as x approaches 5 for g of x. So here's f of x. We want is approaching 5, so here's 5, so the limit is 2. So 3 times 2, which is 6. And then for g of x, we want to approach 5. Here's 5, and from both sides it's 4. So 2 times 4, which is 8, and 6 minus 8 is negative 2. Now we're separated with just subtraction, so the limit as x approaches 5 from the left of f of x minus the limit as x approaches 5 from the left of g of x. So 5 from the left is 2, and 5 from the left is 4, and 2 minus 4 is negative 2. Now we have a division, so I could say this is 3 times the limit as x approaches negative 7 for f of x. And because I wrote too big, I'm just going to write divided by the limit as x approaches negative 7 for g of x. All right. So f of x, we'll scroll up here, and we want negative 7, which is right here. And that limit looks to be 5. All right, so because I'm out of space, 3 times 5 is 15. And now negative 7, and we're approaching what looks like 3. All right, so 15 divided by 3 is 5. All right, let's separate these out. We got 4 times the limit as x approaches 3 of f of x times the limit as x approaches 3 for g of x. All right, well, I'm looking here at g of x. Here's 3. The limit from the left and the right do not match. So that limit doesn't exist here. Doesn't exist. And because of that, doesn't matter if this is a number or not, the entire thing can't exist if one piece of it doesn't exist. All right, f of x squared. Limit as x approaches negative 3 of f of x squared. We can actually say that we can find the limit as x approaches negative 3 of f of x and then square that entire answer. So negative 3. Negative 3 looks like negative 6. So we can do negative 6 squared, which gives me 36. All right, we have the square root of, the limit as x approaches 4 of the square root of 8 times g of x. So really, we can take the square root of the limit as x approaches 4, and really, let's move that 8 out front. 8 times the limit as x approaches 4 for g of x. Let me erase some drawings here. So at 4, the limit looks to be 5. Am I reading that correctly? It looks like 5. So we'd have the square root of 8 times 5, which is the square root of 40. And let's just go ahead and simplify that. I could break that into 4 times 10, so 2 root 10. Okay. The limit as x approaches negative 3. All right, negative 3 here on g of x doesn't exist, right? We've got two things going different directions. So the whole thing won't exist. All right, we have a division here. So the limit as x approaches 6 for f of x over the limit as x approaches 6 for g of x. Because I'm right here with g of x. The limit as x approaches 6 from the left and the right is 5. Let's go to f. As it approaches 6. And that was 6, or was it negative 6? Okay. 0. And 0 over 5 is 0. All right, the composition here, we can do the limit, or we can do the function value of the limit as x approaches negative 2 for g of x. So let's see, as it approaches negative 2 for g of x, looks to me like negative 3. All right, so then f of negative 3 is, looks like 6, negative 6 to me. Negative 6. All right. Let's maybe do some from a number perspective. I almost was going to say equation, but we don't have equations yet. So we have the limit as x approaches c for f of x is 3. The limit as x approaches c for g of x is negative 2. And the limit as x approaches c for h of x is 4. So let's continue to apply these properties. All right, so we have 3 times the limit as x approaches c for h minus 2 times the limit as x approaches c for g of x, and then we can square root the whole thing. All right, so 3 times the limit for h, it's 3 times 4, which is 12. And the limit for g is -2. And 2 times -2 is going to be -4, but I have that negative in front, so it's really going to be 4. And then that gives me a square root of 16, which is 4. All right, so we have the limit as x approaches c for f of x times 5 times the limit as x approaches c for g of x. So f was 3. And then we have 5 times g of x, which was -2. So 3 times 5 times -2. So we have 15 times -2, which is what, -30. All right, we have a quantity squared, so we can actually square the whole thing at the end. So we have the limit as x approaches c of 7 minus the limit as x approaches c for g of x. So remember, a constant is just a constant, so 7. And then g of x was -2. So 7 minus -2 is 9. 9 squared is 81. We got a big complicated one here. So we can just basically distribute that limit to every piece. So 2 times the limit as x approaches c for f of x plus 3 times the limit as x approaches c for h of x divided by the limit as x approaches c for h minus the limit as x approaches c for g. So 2 times f, 2 times 3 is going to be 6, and 3 times 4 is 12. H was 4, G was -2. 6 plus 12 is 18. Add that, we get 6. And final answer of 3. Alright, let's go for some more. Oh, it's just 2 more before moving to something different. Okay, so we got the limit as x approaches c for h of x times the limit as x approaches c for f of x plus, and really I should do this first because it's in parentheses, the limit as x approaches c for 6. So h was 4, f is 3, and then that's a constant, so that is just 6. 6 plus 3 is 9. 9 times 4 is 36. All right, we've got the limit as x approaches c for f of x squared divided by the limit as x approaches c of 4 minus the limit as x approaches c for g of x. So f was 3. 3 squared is 9. 4 and g was -2, so I get 9 over 6, which I can reduce that to 3/2. All right, so I'm going to go a little bit further with the limit of these composite functions. All right, so provided the outside function is continuous at the limit of the inside function, we can use this. Right, so f and g are functions such that the limit as x approaches c of g of x is L. Remember, L is a real number. And then the limit as x approaches L of f of x is f of L. Then our composite, the limit of the composite, is f of L. A lot of words there. All right, so our problem occurs if that f of x is not continuous at x equals L, or the existence of the limit of g of x at x equals A. All right, so we'd apply the if and only if definition, which is that that right side exists. So the limit as x approaches c for f of x is L is the same as the limit as x approaches c from the right of the function. Then the limit as x approaches c for f of x is L. Alright, so let's look at a few. Alright, so the limit as x approaches 1 of f of x. So we can see that we are not continuous at x equals 1 because there is a hole there. So what we're going to do is we're going to fix that by saying, all right, let's do a little u substitution here and say that u is going to be the inside. So the limit as x goes to 1 for f of x. All right, so let's look at that. So from the left and from the right, we are approaching -2. I'm going to add in this little piece that we are approaching -2 from above. All right, and that's going to be important for this next step. So, all right, if we apply this u rule, we can say, all right, the limit as x approaches 1 for f of u. And I don't know why I put in x goes to 1 because I'm in terms of u. So we want to use this. So as u goes to -2, and then from above. So if I look here at -2, right, normally we would say, okay, it doesn't exist, but we have this condition here of from above. So we want the from above part. So this is 4. So because of all of that, we say the whole thing is now 4. Okay? So let's look at another one. So there's another case where at 0, the function value is undefined. So I'll do the inside, right? So u is going to be the limit as x approaches 0 for f of x. And in this case, we're approaching 3, but from both sides, both above and below. So from above and below. So we're going to have to check 2 things. So we want to check the limit, again, I'm going with x, as u goes to 3 from the left and the right. We want to check both directions because we are approaching from above and below. So, all right, 3 from the left is 3, and 3 from the right is 1, and they do not match. So this entire limit does not exist. Right? Let's look at some more. Both of those were examples where it was like a function within a function of itself. So let's look at some different ones here. All right, I should have left myself some more space with these. All right, this first one's not a very good one because it's another f of x, but it's okay. Let's do the inside. So u is going to be the limit as x approaches 1 for f of x. So 1 is what? -3. But from above, because both are coming from above. So then we want the limit as u approaches -3 from the right for f of x. So 3 from the right. Sorry, -3 from the right, which is going to be 2. So that entire limit is 2. All right, now let's do the limit as x approaches 2 for h of g of x. All right, so we're going to let u be that inside one. So the limit as x approaches 2 for g of x. All right, so g of x for as it approaches 2 has 2 different answers, right? So we have 2 different u's to use. Sounds crazy. So we'll do from the left first. So from the left, it's at 3, and it's approaching it from below. And then we can let u be the limit as x approaches 2 from the right for g of x, and that's going to be 1. Actually, it's also from below. Don't know where I wrote above. As it's coming from below, we're going to want to use the left side. So now when we go to do the h of x part, we'll do both. So we have the limit as u goes to 3 from the left for h of x. So 3 from the left is going to be 4. And then I've got to do the other one. So the limit as u goes to 1 from the left for h of x. And 1 also goes to 4. And these are the same. So the entire limit is 4. Alright. Alright. So we've got u is going to be the inside. So the limit as x approaches -1 for h of x. So if I go to h of x, -1, ooh, I'm hitting -4 from above. So the limit as u goes to -4 from the right for g of u. And I'm just realizing right now I kept putting x for these. And I need to put u to be in proper notation here. My bad. So g is the middle one. We want -4, and we're going from the right. So that's going to be -3. So the whole thing is -3. All right, hope I left myself some more space. Oh, just a little bit here. To do it again with a different set of graphs. Alright, so we are going to have u be the inside. So the limit as x goes to -3 for g of x. So -3 looks like -4 from above. So now we'll look at the limit as u goes to -4 from the right for f of x. And I really mean f of u, but using the f of x graph. So -4, and then from the right, so it's going to be -1. So the whole limit is -1. So get f of g as it's going to, x is going to 2. So u is going to be the inside. So the limit as x approaches 2 for g of x. So 2 is 4 from below. So that the limit as u approaches 4 from the left for f is, let's see, where's 4? And from the left, it's going to be 3. So the whole thing is 3. All right, this one is a little bit of a different case because we could say that u is the function 8 minus x squared, right? So it's a downward facing parabola, right? Let's shift it up some. So we could say, all right, it's a polynomial, and as it's continuous, so 2 from the right is going to be the same no matter what. So I can just substitute in 2. So I get 8 minus 4, which is 4. And since it is looking at the directional side, so from 2 from the right, and it's approaching 4 from below. So then we can do the limit as u approaches 4 from the left for f using our u. So f function, and then 4 from the left, it's going to be 3. Right? And then with this one, we can separate it out and say, all right, u is going to be the limit as x approaches -4 from the right for 2, plus the limit as x approaches -4 of the right for f. So that's going to give me 2 plus, and let's see, -4 from the right is going to be -1. And 2 plus -1 is 1. So the limit as u goes to 1 for g of u is 2. So that whole thing is 2. All right. I also love that this section is called Intro to Limits, and I'm doing literally everything about limits. So, for the sake of this being a long video, because I'm already at 42, what do I have left? 1, 2, oh, I only have 3 pages left. I'm going to leave it in one video. Alright, so the only thing we have not done yet is seeing an actual function itself. We've seen graphs and we've seen with the properties, but we haven't actually looked at an actual function equation. So the way we can solve these is called an analytical method, or methods, I guess. So what we want to do first is we want to try a direct substitution. If we have the function, I mean, when we're looking at the graph, we're looking at, all right, let's find the x value, let's see where it approaches, and we can see visually. Well, if we have an equation, we can try substituting in an actual value, because if the function is a continuous function, then the directional limits will be the same. And yeah, if for whatever reason, if we plug in doing a direct substitution, we get an indeterminate form, which is 0 over 0 or infinity over infinity, something like that, then we can try some algebra manipulation, try see if things cancel out, and then try again with the direct substitution. And if that doesn't work, we can try some other methods. All right, we might try to rationalize. So let's see. So if f is a polynomial function or a rational function, then the limit as x approaches c for f of x is f of c, provided that if f is a rational function, the value of the denominator does not equal 0. So this first one here in part A, we have the limit as x approaches 2 of a quadratic. It's a polynomial, it's continuous everywhere, so the direct substitution should work. So what I'm going to do is I'm going to do an equal sign, and I'm going to substitute that in. When I'm doing a substitution like this, I can drop off the limit symbol. So I get 3 times 2 squared minus 5 times 2 plus 4. 2 squared is 4. 4 times 3 is 12. minus 10 plus 4. 12 minus 10 is 2. 2 plus 4 is 6. All right, let's see what I get here. I get 2 cubed plus 1 over 2 plus 1. That's 8, so 9 over 3, which is 3. So that's perfect. All right, natural log of e, and then 3e. Natural log of e is 1, and 1 over 3e. All right, let's see. Cubed root of 4 plus 4, which is the cubed root of 8, which is 2. So all of those had worked out very nice. So, okay, if we get 0 over 0 or infinity over infinity, where the goal is to try and simplify. So, always try the direct substitution first. So 4 squared is 16 plus 4 is 20 minus 6. 16 plus 4 is 20. 20 minus 6 is 14. And then 4 squared is 16. 4 times that is negative 24 plus 8, which is going to give me 0. So it doesn't necessarily give me that 0 over 0 or the infinity over infinity, but I do have a 0 in the denominator. So I can think about what this function is and think, oh, if it's giving me a 0 in the denominator, then potentially it's a vertical asymptote. But let's try and factor. So because the direct substitution didn't work, and I'm going to try factoring, I need to keep that limit notation. So let's see, the numerator, I could probably factor that into, let's see, 2 numbers that multiply -6 and add to 1 is probably 3 and 2, and I want a positive in the middle. And then the denominator, we get what? Probably 4 and 2. And we want negative in the middle. Oh, negative for both. So if I cancel out this factor of x minus 2, I'm left with the limit as x approaches 4. And I have x plus 3 over x minus 4. And if I substitute in the 4, I'm still going to get a 0 in that denominator. Let's see, I'd get what? 7 over 0. So I've done all the algebra manipulation, so I would say does not exist. I guess I should really say doesn't exist. I mean, there's a vertical asymptote, but I guess a limit is what is the function doing? I'm going to put positive or negative infinity. But, yeah, actually, no, we'll say it doesn't exist. Because this is the general. It's not the sided limit. This would have to be a sided limit for it to exist. I'm going to leave it at that. Which leads me into this next point of finding the sided limits. So, okay, it's the same function. So we already know it simplifies down to the limit as x approaches 4 from the right of x plus 3 over x minus 4. So to find the one-sided limits, we want to see what's happening to the right of it. So we want to pick a value to the right. So let's use, how about 4.1? So when we do the direct substitution, 4.1 plus 3 over 4.1 minus 4. I'm just looking for the signs because we know in this case we have a vertical asymptote, right? So we just want to know whether we're going to positive infinity or negative infinity. So I'm going to have a positive number over a positive number. So I'm going to go off to positive infinity. And because this is the same function, If we know the behaviors of vertical asymptotes, if their multiplicity is odd, they're going to go in opposite directions. So my prediction is this is going to go to negative infinity because it's got to be the opposite of the other. But we know, all right, limit as x approaches 4 from the left for x plus 3 over x minus 4. Now we want to pick, ooh, that's supposed to be a minus. To the left of 4. So how about 3.9? So 3.9 plus 3 over 3.9 minus 4. It's going to give me a positive over a negative. So it is going to give me that negative infinity like I predicted. Right? So we can find one-sided limits because at this point it's telling us what's the behavior of the function. So the general limit, because they are opposites, doesn't exist, but these sided ones could. Okay, find the limits analytically of the piecewise and show the steps. Alright, so we want as x approaches 1. So we've got two different sides. We got greater than 1, less than or equal to 1. So we want to see the limit as x approaches 1. We want to check the directions. And if they're the same, then the limit exists. So from the left of 1, it's going to be the less than 1. That's x plus 1. And so from the right, it's going to be that x cubed plus 1. Right? So I can plug in doing a direct substitution and see what the value's approaching. So this one will give me 2. And this one will also give me 2. So they are the same. So that limit is 2. All right, same idea here. Got to check the sides. So the limit as x approaches 2 from the right. And as it approaches 2 from the left. So left is the x squared minus 4x plus 7. And right is the negative x squared plus 4x minus 1. We can try the direct substitutions here. So it's going to give me negative 4 plus 8 minus 1, which is 3. And then this one will give me 4 minus 8 plus 7. So negative 4 plus 7, which is also 3. So they're the same. So 3. All right, got some complex fractions here. So I like to do is get it into one fraction, or try to at least. So for just this bottom piece, all right, I've got 1/4 plus 1 over x minus 4. I'm going to combine them into one fraction. So the common denominator that I need is going to be 4 times x minus 4. So this first fraction is missing the x minus 4, and this second one is missing 4. So my common denominator, like I said, is going to be 4 times x minus 4. And then the numerator, I'll have x minus 4 times 1, so x minus 4. And then I'll have 4 times 1, which is 4. So I'd really get x over 4 times x minus 4. And that is the denominator. So I have the limit as x approaches 0 of x over 4, x minus 4. All right. And then for these kind of fractions, we could say that the x on top is really x over 1. And then I was always taught to simplify a fraction over a fraction by big C over little c. So I'd have the limit as x approaches 0 of big C, which is 4 times x minus 4 over little c, which is x times 1. And then I could cancel out those x's and get the limit as x approaches 0 of 4 times x minus 4 and do a direct substitution, right? And we'd have 4 times 0 minus 4, which is negative 16. Right. So let's try it again on this one. So this numerator, that first fraction is going to need 2, and that second fraction is going to need that 2 plus x. All right, so my common denominator is 2 times 2 plus x. My numerator is now 2, and I'm going to subtract both of those off. So it's going to be subtract 2, subtract x. So really, negative x over 2 times 2 plus x. So I have the limit as x approaches 0. My numerator is now negative x over 2 times 2 plus x all over x. I can do that same thing and say x is over 1, and then do this big C over little c. I guess I never really said why that big C over little c works. But we would have, you have to multiply by the reciprocal. So you'd have the negative x over 2 plus 2x, and then you'd have to be multiplying by 1 over x. And if you do that, you're going to get the same pairing up as this big C over little c. So the limit as x goes to 0 of negative x over 2x and times 2 plus x. So I can cancel the x's out. So the limit as x approaches 0 of negative 1 over 2 times 2 plus x. And then I can do that direct substitution. And I get negative 1/4. All right. All right, last page here. We have the conjugate or rationalizing method. So what happens here is if we have a square root, there's numerator or denominator, we're going to want to try and do our best to get rid of it. Because our goal here is to be able to cancel out a factor. Like we're going to want to cancel out this x plus 1 because it's creating that 0 in the denominator. And we might be able to get that from doing the rationalization or the conjugate method. So conjugate is we would be multiplying by same thing, different sign. So because this is minus, we're going to multiply it by the plus. And what I'm going to do here is the denominator, I'm going to leave this as x plus 1 times the square root of x plus 2 plus 1, because that x plus 1 factor might cancel out. Because up top, if I do this multiplying out, square root times square root is going to give me what's under the square root. And then I would have plus the square root of x plus 2, and then I would have minus the square root of x plus 2, and then I'd have minus 1. So that I get the limit as x goes to negative 1. That numerator will simplify to x plus 1. That's why I didn't bother multiplying out the denominator, because those factors right there are going to cancel out. So I'm left with the limit as x approaches negative 1. There should be an equal sign because I'm following my path here, of 1 over, and then square root of x plus 2 plus 1. Then I can do that direct substitution. So square root of 1 plus 1 to give 2. So final answer of 1/2. Alright, so let's do that again on this problem. So I'm going to rationalize or use the conjugate method here. So I'm going to multiply both by 3 plus that square root of x plus 4. I'm going to leave the numerator as x minus 5 times 3 plus the square root of x plus 4. And the denominator, I'll have 9. That middle term will cancel out, and then I'm left with minus that x plus 4. So I have the limit as x approaches 5 of x minus 5 over, times, 3 plus the square root of x plus 4 over, and that's going to give me negative x plus 5. But if I take out a negative, then I get x minus 5 to then be able to cancel out. So I get the limit as x approaches 5 of 3 plus the square root of x plus 4 over negative 1. So then I get, let's see, I can do a direct substitution. So 3 plus the square root of 5 plus 4 over negative 1 is going to give me 3 plus 3, which is 6 over negative 1, which will give me negative 6. All right, last few here. I'm going to try direct substitution in here and see what happens. So 5 times 3 is 15. 15 plus 1 is 16 to the 2/3. I don't know what that is off the top of my head. 16 squared is what? 256. Then we're doing cubed root. That was 16 times 16, which is 4 times 4, and 4 times 4, taken out in groups. So 4 cubed root of 4. Alright, if I substitute in 3, I get a denominator of 0, and I don't want that. But I see a square root in here, so let's go ahead and try it and rationalize. So square root of x plus 1 plus 2. So I get the limit as x approaches 3. That numerator is going to be x plus 1, and then minus 4 over x minus 3 times that rationalization. That numerator is going to be x minus 3. That factor is going to cancel out. And now I can do a direct substitution. So square root of 4 plus 2 is going to give me 2 plus 2. So 1/4. Alrighty, then last one here. If I do a direct substitution, I have a denominator of 0. So I'm going to want to try and do some algebra here. Go ahead and square that out. So I have the limit as h approaches 0. It's going to give me x squared plus 2xh plus h squared. Distribute that negative 3. So minus 3x minus 3h. And then I'll subtract x squared and add 3x. It's all over h. I think I'm going to have some terms that might cancel out. So I have x squared minus x squared, negative 3x plus 3x. So I have the limit as h goes to 0 of 2xh plus h squared minus 3h all over h. I can factor out an h from each of those to be able to cancel out with the bottom. So I have the limit as h goes to 0 of 2x plus h minus 3. And then I can do a direct substitution of plugging in 0. And I'm left with, I'll put it here, 2x minus 3. And we'll see that that is okay to have. So, all right, that was a long intro to limits, but let me know if you have any questions.